Hello, my name is Mirza. This presentation is regarding ANRF PMECRG project, and the title of the project is Static and Dynamic Graph Queries in the Classical and Quantum Bitprobe Model. So, suppose we wish to answer millions of queries in massive network. In a social network, the query could be, is Alice connected to Bob? In routing and logistic network, we do have queries like, is road UV open, or is server V near you? Or in general, we want to know that whether UV is an edge in a graph. So modern graph have billions of edges, and we want to know that can we answer queries using very little memory and few bit probes. So these graph queries can be modeled as a set membership problem. So for example, our edge set could be all edges of the graph, and then every edge is simply an element of the set EG. And we want to know that given a vertex U and V pair, we want to know that is UV belonging to the edge set of the graph. And so it's kind of a membership queries, same as given a subset from a universe of size M, we want to store it and answer that whether X belongs to S or not. So here S is equal to EG and X equal to UV. So many graph queries such as X, existence, and adjacency queries can therefore be answered using efficient membership data structures. And in Bitprobe model, we study these problems. So in Bitprobe model, we are given a universe of size M, and we want to store a subset of it whose size is less than or equal to N, and then given a X belonging to universe U, we want to answer that whether X belongs to S or not. So the data structure consists of table of S bits, and a query algorithm may inspect only T bits of this table. And we also have computations are free, only memory access are counted. And the goal is to minimize S value using at most T probes. So formally, given a subset of size at most N, we have a storage scheme, which is basically a function which maps all possible subset of size N to S bits, and a query scheme which takes an element X belonging to M, and then it gives you T locations in those S bits. And then you read those T locations and then compute some Boolean functions, which evaluates to 1 if and only if elements belongs to the set given to be stored. So our research goal is to develop efficient classical and quantum bit probe schemes and study the trade-offs between storage and query complexity. So our query need not be constant, and the applications, we want to investigate how these bit probe techniques can be adapted to graph query problems such as edge membership, neighborhood queries, static and dynamic graph representations. And so just to understand that how the Bitprobe scheme works, let us take some trivial solutions. So we are given a subset S from a universe U, which we want to store, and the size is at most N, and we want to answer the query is X belonging to S. So what we do is that whatever the set is given to us, we store them in a sorted order in an array, and the amount of space required will be n into log m, because the size of the universe is m. So each element required log m bits. And then we can do a binary search on those array. And to extract one element, we need log m queries. So that's why for binary search, we need log n and log m bits to extract one element. So here you can see that the space is really good, but the query is huge. The other trivial solution could be that we have n-bit array, and if the element is present, we write 1 there, otherwise we write 0. So basically, ith bit is 1 if and only if I belong to S. So here the space is M, but the query is just 1. So what we are seeing here is that the query is really nice, but the space is huge. So basically, we study the trade-offs between space and query. So here we are answering a question that we want to store one element from the universe of size M. And we want to see that what is the minimum amount of space we take. So for example, here we map all the M elements on a square grid. And what we do is that for each, and we are basically partitioning the universe of size M. So X1 will have all these elements, X2 will have all these elements, and so on. So here you can see that the red color element is given to be stored. And what we will do is that for element given to be stored, we will set x3 equal to 1 and y2 equal to 1, and rest everything will set to 0. So that if a query is asked for those elements, given a query element, we go to the X type set and Y type set. If both are 1, we say that the element is present. Otherwise, we say that the element is not present. So here you can see that using root m queries, root m space or order root m space, we are able to answer the queries. We are able to answer any queries from the universe correctly. So yeah, so to store one element, there is a generalized scheme using tpros, which takes t into m raised to power 1 by t space, and the lower bound of this scheme is mapped with the upper bound. So n equal to 1, the problem is settled. You can see that the previous scheme cannot store two elements, because if suppose these two blue color elements were present, so it will take, then what we'll have to do is that we will have to set x and y both to be 1 for this blue color element. And because of that, this red color point will take x, y from here and x from the other blue point. And same for this guy. So this will take x from one of the blue point and y from another blue point. And hence we will answer incorrectly for these red points. So that's an issue. So now we want to see that can quantum queries do better? And in quantum Bitprobe model, the memory remains classical, only the query algorithm is quantum. And the query algorithm may inspect several memory locations in quantum superposition before making any measurements. So the question that you want to answer is that can quantum queries improve space trade-offs, space query trade-offs? So the question was initiated by Radhakrishnan and others. So here you can see that to map, again, we are mapping all the M elements on the square grid, and we are again having 4 tables. So for the element which is present, so for example, here this Ij and Rs, what we do is that for the element that is present, we set xi equal to 0 and yj equal to 1. And then for this red color point Rs, we set xr equal to 1 and ys equal to 0. And in the other table, x prime, y prime, we set xi equal to 1, y prime j equal to 0, and x prime r equal to 0, and y prime s equal to 1. And rest every other bit is set to 0. And what we do is that given a query element uv, what we do is that we calculate xu. So we figure it out the x type set and y type set to which it belongs, and then we calculate the XOR of these two guys. And then for the second probe also, we look into the x prime u and y prime v, and then again we compute the XOR of these 2 bits. So in quantum, like you can create, you can compute the XOR of 2 bits using one quantum bit probe. Again, you can compute the XOR of these 2 bits using one quantum bit probe, and then we take the AND of these 2 guys. So you can see that, so the membership answers correctly for the element Ij and Rs, and you can see that for all other elements also it answers correctly. So this was just one configuration. The element could be any other configuration, and then accordingly you can set bits. So what we have seen is that classical Bitprobe schemes achieve remarkable space efficiency, and quantum queries can further improve the space query trade-offs while keeping the memory classical. So the research question is the following: can better classical Bitprobe scheme be designed, and when do quantum queries provide genuine advantage? And can Bitprobe techniques be extended to static and dynamic graph queries? And what are the corresponding lower bounds? So thank you.